Welcome to Lesson 5.3 for Business Calculus. Today we're going to talk about related rates. All right, related rates problems involve the rate of change of two or more related variables that are changing with respect to time. Note that you need implicit differentiation to solve these problems. All right, so let's talk about our approach to solving related rates problems. The first thing you need to do is identify all given quantities and quantities to be determined. Then you want to write an equation involving the variables whose rates of change either are given or yet to be determined. Use the chain rule, implicitly differentiate between both sides of the equation with respect to time t. After completing step 3, substitute into the resulting equation all known variables and their rates of change. Then solve for the required rate of change. Okay, let's look at a review problem. We're going to consider the sphere of a radius of 10 centimeters. If the radius changes 0.1 centimeters, a very small amount, how much does the volume change? All right, so we know volume is equal to 4/3 times pi times r cubed. So the derivative of the volume is going to be, using the power rule, we do 3 times 4/3 to get 4, and then pi r to the second power, but then we also need to have the derivative of r. So let's plug in what we know. So we're going to have 4 pi times 10 centimeters squared times the derivative of r, which is the rate of change, so times the 0.1 centimeters, and we get that that dV is equal to 400 pi centimeters cubed, and so we know the volume would change by approximately 40 pi centimeters cubed. Now, let's look at the rate, what's happening if the radius is changing at an instantaneous rate. Okay, so it's going to be a variable rate, but at the instant that we're talking about, it's 0.1 centimeters per second. So this is possible if the sphere is a soap bubble or a balloon. Those kind of things can happen. So our volume is still 4/3 pi r cubed. The difference this time is we want to do the derivatives with respect to time. So we want dv dt, and that's still going to be 4 pi r squared by the power rule, times the derivative of the radius with respect to time, so dr dt. So dv dt is going to be 4 pi times 10 centimeters squared, and since our instantaneous rate at this point, our dr dt, is 0.1 centimeters per second, we plug that in, and we get 40 pi cubic centimeters per second. So the sphere is growing at a rate of 40 pi cubic centimeters per second, and this is an exact answer, not an approximation like we got with the differential problems. All right, water is draining from a cylindrical tank at 3 liters per second. How fast is the surface dropping? So we are looking for the difference in height as it relates to time. So we know the difference of volume in relation to time. We know dV dt is -3 liters per second. Since height will be in centimeters, let's change liters to cubic centimeters. So let's scale for that. And so each liter is equal to 1,000 cubic centimeters. So we have -3,000 cubic centimeters per second. We want to know, like I said, dH dt. Okay, we want to know how fast the surface is dropping as a function as it relates to time. So we need a formula to relate V and H. We need something that connects volume and height. Volume of a cylinder is equal to pi r squared H. All right, so dV dt is going to equal pi r squared because that's just the coefficient there, dH dt. So we've got negative 3,000 cubic centimeters per second equals pi r squared dH dt, because we know that dV dt is that negative 3,000 cubic centimeters per second. That's why we placed it in there. So when we solve for dH dt, we get that it's 3,000 cubic centimeters per second divided by pi r squared. All right, again, the steps for related rate problems are going to be to draw a sketch if you need to, write down the known information, write down what you are looking for, write an equation to relate the variables, differentiate both sides with respect to t, and evaluate. All right, let's look at the truck problem. Truck A travels east at 40 miles per hour, and truck B travels north at 30 miles per hour. How fast is the distance between the trucks changing 6 minutes later? Okay, we know that rate times time equals distance. All right, so for truck A, we're going to have 40 miles per hour times 1/10 of an hour, because 6 minutes is 1/10, and so we get 4. So that's how far away from the starting point A will be. Okay, so let's do the same thing for B. So 30 times 1/10 equals 3. Again, we're doing 1/10 because 6 out of 60 minutes gives us 1/10 of an hour. So we have y equals 3. What we want is the rate of change between A and B, but before we can find that, we need to find the distance between A and B. So with the Pythagorean theorem, we know that 3 squared plus 4 squared equals z squared if z is that the distance we're interested in. So 9 plus 16 equals z squared, 25 is z squared, so z is 5 because it has to be positive. All right, awesome. Now that we have those values, we can start looking at what is going on as far as the how fast the distance between the trucks changing 6 minutes later. All right, let's look at x squared plus y squared equals z squared. That's our relationship that we have because they are making a right triangle. Let's take the derivative of all variables with relate to time. So we're going to have 2x times dx dt plus 2y times dy dt equals 2z times dz dt. All right, we can divide both sides by 2 and just get rid of all the 2's, just clean it up a little bit. Dx dt is 40 miles per hour, and x is 4. Dy dt is 30 miles per hour, and y is equal to 3. All right, so we're going to have 4 times 40 plus 3 times 30 equals the 5 that we know. We don't know dz dt right now. So we're going to get 250 when you evaluate the left-hand side equals 5 times dz dt. So we need to divide both sides by 5, and we get that 50 is equal to dz dt. So 50 miles per hour is how fast the trucks are, how fast the distance between the trucks is growing 6 minutes later. All right, guys, go ahead and print out your problem set and get started on the problems. If you have any burning questions, you know how to find me. Otherwise, I will see you in class. And thank you so much for watching the video. Have a great day.